Good morning. Welcome to Krishna's classroom. Let us recall what we did last time very briefly. We have a measure space X mu then of course we have the following X mu star its completion. In the last lecture we were exploring why do we go for the completion of the space. Now here what happens is that mu star restricted to M. This is the connection between mu star and mu. And later on, when we start working on other things, we will be simply writing, we will be a priori just assuming that xm mu is a complete measure space. Now, one thing that we have proved is that taking into account the concept of sets of measures 0, we have a completion of the given measure space that is denoted by x m star. M star is a bigger collection than m, and m is contained in m star. So this is what you have. That means we brought in some extra sets into the sigma algebra and enlarged it so that now a larger collection of functions is measurable. In fact, all the functions which are measurable under xm mu is now measurable in xm star mu star. Not only that, you have a larger collection of functions measurable. Now, this is the advantage that we gain. And in fact, you see that if f is a measurable function, if f is a measurable function in mu, then it is measurable in so all measurable functions on xm mu are measurable now in xm star mu star with the same measure. But there exists functions which are measurable in xm star mu star which are not necessarily measurable in xm. Now the whole reason why we did this exercise of completion was to ensure that we are comfortable while doing integration. Okay. So what we did was we looked at a subclass of functions. So we will take f or even extended real value functions. Not necessary. extended real value functions. Suppose E is a subset of X, E is measurable, and mu of E complement, that means its complement is having zero measure. Now we take F, all functions. Assume F is such that, we are not assuming this is measurable, not necessary. Measure. Assume F is such that F inverse of V intersection E is measurable for every open V in the range. Okay. Then F is not measurable. What we are assuming is that F inverse of V, its intersection with E is measurable. That means the portion of F inverse of V trapped in E is an element of F. This is what we are assuming. So you see, you can actually see the following. Restrict to E. Okay. Talk about all measurable functions on E. Right? Now extend it in an arbitrary way to the whole of X. Can you assure that it is measurable? It may not be. Even if this condition is satisfied, it may not be measurable. Because you can always construct the following and take F contained in X such that E is contained in F is contained in X, okay, properly contained X. And assume that F not such a set. Now what one does is, we keep the function F, and on F slash E, so we take G from X to E, X to the extended real line, such that G is such that G is equal to F on E, and G is a constant, some constant C on F slash E, and G equal to C2. ഞാൻ പിന്നെ വിളിക്കാം ക്ലാസ്സിലാണ്. G equal to C2 on F com. Remember, this assumption is that f is not measurable. Then one can easily see that G is an extension of f to x measurable. So what we did was, we are now trying to exploit that mu of E complement is 0. Okay. The difficulty that you face is the following. That is, you cannot assure that mu of a set of measure 0 is measurable. The difficulty is the problem is that a of a now what one does is we rectify this defect. What did we do? We take a sigma algebra which is m star. So define m star the set of all the set of equal to 0 and on this we set mu star of E equal to mu of. This is the completion. So we have already proved everything. So I don't want to repeat it. Then of course, then what you have is this. We have proved already that okay. Now what we do, so having got this, what we have obtained is this, that the collection M star is a sigma algebra, and mu star is a mu to E star. In fact, what happens is x star is a metric space. It is an extension of this is a completion. This is the completion. Now clearly, okay, what are the consequences? Let us just write down. Then, first thing that you observe is that all subsets of zero measurable now measurable and measure of such sets having zero measure. By design. Okay? And the immediate consequence of this facility is that the consequence is that any measurable, any function with F restricted to E, measure of E complement E, 0. Measurable has any extension of it to X, irrespective of what F takes. Complement. Measure. Okay. Now this is the greatest advantage. So without any inhibition, you can say that. Thus, we can say that if F and G agree on the same on E, with the measure of E complement equal to 0, then they are, we say that F is equal to G almost everywhere on. Okay. So if F is measurable, then G is also measurable. Okay. So if F is equal to G, then both F and G are, then G is measurable. If F is, and vice versa. This is the advantage. All extensions of F are now okay, right? Therefore, on the other hand, as far as integration goes, both F and G have the same integral. When G are concerned, integral of F dV is This is equal to. And now this is the advantage that you have. So all extensions of f are now integral. And they have the same integral as that of f. Okay. So all extensions. Okay, let me just make it clear with a chair. This is your x. Now this is v. You have an f here. So now you take f and take f restriction and extend it g on in any way you like. That means f and g differ on E column. Still, integral of x integral of okay. So all extensions of f are now measurable in the completed space. Okay, and they have the same thing. This is that one. In this background, we shall assume that the given given measure space. That means we have given justification for all this. So I don't want to do it. Okay. Now what we want to examine is the following. You recall we had this monotone convergence theorem, dominated convergence theorem, two hallmark results and their consequences. This was stated for without taking into consideration the sets of measure 0. Okay. Now what we are going to do is we are going to, it's all coming from our experience of working on Riemann integral itself, because you see that if you take a Riemann integral function and then on a null set, if you just modify it, that is also Riemann integrable, and the two Riemann integrals of the two functions are the same. So we are going to do this sort of thing. Okay, right? Now on the complement of a set, on the complement of a measurable set whose complement has measure 0, one can modify the function in any way, okay, right, and then get the integral without any change in the integral. This is the moral of the story. Okay, what are the consequences? Now the question that we ask next is, how do some of the basic theorems get modified? The question. Standard theorems like monotone convergence theorem, or dominated convergence theorem, get modified. This is what we are going to examine. Okay, let us just recall what the Lebesgue dominated convergence theorem is. The monotone convergence theorem, just let us recall. Then we look at the dominated convergence theorem, and okay, let me recall. Which we have proved earlier. Okay, what does that theorem say? So theorem is this: monotone convergence. Let Fn be a sequence of measurable functions on X, and such that A infinity. This is important for every X value. B Fnx converges to Fx infinity. Here convergence takes a larger meaning, that it may take some. Okay, right. For every belonging to X. This is again important. For every X belonging to X. Then we conclude that measurable and this is the theorem that we have proved earlier. Okay, in the light of what we did, how would the modification would look like? This is what we want to examine. First of all, we are now going to enter a liberal environment. What we are going to assume is that instead of the condition A is valid for every X belonging to X, we assume that this condition is satisfied almost everywhere on X. No modifications. Now, assume A to be valid almost everywhere. On X. That is the measure of the set on which so we assume the modification, we assume A to be valid almost everywhere. What does it mean? That A is valid on a measurable set and measure of E complement is the meaning of that. That's the first change. The second change is again B also be modified is valid almost everywhere on. So instead of valid everywhere on X, we just make this assumption. Then we can conclude, arrive at the same conclusion on integrals. And their division. So this is possible. Okay, so let us do that. Now look at the now a consequence of this is then okay, take the dominated. What is the dominated convergence theorem? The dominated convergence theorem which we have proved already reads as dct. Okay. Suppose is a sequence of complex measurable functions on X such that is assuming pointwise convergence for every X belonging to X. This is the crucial thing that okay. If a function L1 mu exists such that all these fn's are dominated by G and X belonging to the whole of X. This is the important. Okay. Equal to 0 and limit n tending to infinity of integral over X okay. So we modify. What are the modifications? The modifications are on the conditions. What are the conditions in this theorem? Conditions in this theorem are one is this, the other condition is the two conditions star and double star have to be modified. What is the modification? The modification is that for every X belonging to X will be now replaced by this result happens on a measurable subset E of X such that measure of E complement is equal to 0. That means this result is valid almost everywhere on X. The second part is again Fn mod Fn is less than or equal to G on almost everywhere on X, which means there is a subset E which is measurable and whose complement is measure 0 such that on that this function G dominates Fn. Outside what happens? Nobody is bothered. Okay. Even under these circumstances, this liberal environment, you will see that the conclusions of the dominant convergence theorem hold. Okay, so these are the modifications that we are able to do. In fact, this is completely taking care of the situation that we are familiar with from Riemann integral. That means take a Riemann integrable function, modify it on a set of measures 0, you get a new function. That function is also Riemann integrable, and the Riemann integral of both these functions do agree. And all about the convergence, the same sort of results do. Okay, so it is the experience that you have there is now generalized in the new context. Now here you see that we have taken X, then a sigma algebra, and a measure. We have also now assumed that it's a complete measure space. Okay. If so, you see you get lot of freedom to modify things on a set of measures. Okay. So what happens as far as integration goes? What happens on a set of measures 0 is material. This is the consequence. It has very wide and deep ramifications in the definition of L1 space or LP space. All these different kind of spaces in which function spaces which you encounter and you work with. Okay, so let us get a feeling for the proof. Right. So let me write down the new modified theorem. Okay. So one of the theorems that we want to explore today is a consequence of the dominated or the not dominated convergence theorem, but the monotone convergence theorem. Okay. So recall one of the consequences. Consequence of monotone convergence theorem. This is concerning the convergence of a series. Measurable functions. Okay, let me just recall this result. So the theorem that we have already proved is this. Measurable etc. And belonging to X is equal to This is again, see, here you are assuming this. See, how would the modification of this look like? The modification of this looks like this: for every x belonging to x, we will have to replace by almost everywhere. So the modification will be that replace this by almost. Let us write down the modified. But we do it far more generally. Let's look at the modified. Or even to some extent generalized. A sequence of complex measurable functions defined almost everywhere. Now this is one more. Next, such that finite. So first condition. Then the series converges for almost all. That means except possibly on a set of measures 0, comma, f L1 mu and integral of this is equal to sigma n equal to 1 to infinity integral over x right? And of course, this is also a measurable. That's that much. Measurable. and this is true. Okay. Let us now see how we get going with them. And that is a guidance to how you. So your object, see your objective, what is the conclusion? This integration, the equality of the integrals, and that the integration and the summation can be interchanged. That is or the summation and the integration commute together. Now this is what the conclusion is. What do we do? What we try to do is to discover a measurable subset whose complement has, and on which all these results are happening. Okay? Right? Now forget about x. You look at only on E, then the conclusion of the theorem that we have proved earlier holds. Apply that. Okay? Therefore, this integral would hold with x, but then you see that on a set of measure 0, what happens? It is not going to affect the integral. Therefore, you can just replace integration over. So, it's just the problem is solved the moment you discover a appropriate E whose complement is of measure 0. So, let me just make a note, remark. We shall use the earlier version by identifying a measurable set whose complement has measure 0 and on the conditions of the previous results that you can draw the conclusion on E. And on integration on E is the same as integration on E because of the set of measures for E. That's the start. the integrals is the same as the integral so the conclusion. So that's the strategy. So how to find this? That's the question. So let us now go how things do. Now all these results, modifications of the earlier versions are proved. This. So there's a single strategy to address. So we will now take up the be the set on which Fn is defined. So that now put S where so we have for each Fn an S. Okay? And to take the intersection of all this, if each Sn is measurable, their intersection is also measurable. Countable intersection is measurable. And you can easily see that since each Sn complement S, the measure of S is also S complement. Because S complement will be the union of each Sn complement S measures 0. Therefore, sum of the measures of Sn complement is 0. Therefore, the measure of S complement is A. Theorem A is the one that we have proved earlier. So we are now taking E to be not E Now we take E to be measure of E comma. Therefore, the series two converges absolutely. So this is the advantage that you have, and such an F is certainly measurable. E and f x is defined on E. Then mod fx is, these are all complex values. This is non-negative. So that this is what we use. The previous theorems are applied on E as it is, and this conclusion holds. By the dominating function. If Gn well, then we have mod Gn phi, and Gn see, we have reduced everything to E. Okay, by the dominated convergence theorem, E integral over E which implies, as I said, E complement as measure 0. So this the conclusion. Okay. So the mode of approach in the proof is by identifying a set whose complement has measure 0, where the previous versions of once that is done, you can finish it off. Because what comes out is that the modifications you do on a set of measure 0 will not alter the integral at all. Okay. So thank you very much. So I'll come back with some more results of this kind, which will give us some more experience of handling that situations. Thank you very much.